Hi everyone, my name is Rishik and this is my master's thesis, Formalizing YUL in Isabelle. This project is about improving the reliability of smart contracts, which are very critical components of the blockchain ecosystem today. Over the next few minutes, I'll walk you through the motivation behind this work, what I've actually built, and how formal verification can make smart contracts safer, more predictable, and easier to trust before they are deployed. Firstly, let's understand what are smart contracts and why does it matter. Smart contracts are basically self-executing programs that run on blockchain. They automatically enforce some agreements like transferring funds or updating access once certain conditions get met. These conditions are often written into the contract itself, and once they are deployed, the contract runs exactly as coded. There is no need for any manual approval or any intermediary. The problem here is there is very little formal verification of these contracts, which means that we don't have the mathematical guarantee that they will behave correctly in every situation. As a result, we have seen major vulnerabilities exploited. The most famous is the 50 million DAO hack, where a logical flaw in the contract allowed attackers to drain funds. Another big issue has been overflow attacks. I will discuss this in a bit. Now, these attacks don't happen because the blockchain is insecure in its own. This happens because the contract was not mathematically verified. And since everything that happens on blockchain is irreversible, these bugs can turn out to be incredibly costly. Now, as we said before, one of the most well known types of vulnerabilities in smart contracts is the overflow attack. This happens when a number in the contract, let's say a token balance, gets very big and wraps around to zero instead of throwing an error. Like, let's say 0 to 255, instead of going after 255, instead of going to 256, it wraps back to 0. This happened because Solidity before version 0.8 did not automatically check for overflows, and developers did not include product protections. And unfortunately, many attackers took advantage. With this, hackers could steal tokens, they could bypass balance checks, and they could even crash parts of the smart contract. This led to financial losses in many projects. This is exactly the kind of bug that formal verification can catch, and it's a very big part of the motivation behind this project. Now, we have to understand why we chose YUL. When a smart contract is written in Solidity and it's compiled, it goes through a two-step process. Firstly, it gets converted to an intermediary language called YUL and then to EVM bytecode. This is the final low-level instructions that run on Ethereum virtual machine. This Ethereum virtual machine is basically blockchain's execution engine, that it handles all operations like storage, control flow, computation using bytecode. But bytecode, it's extremely low level and hard to formally verify. In theory, we could try to formally verify Solidity itself, but that's very challenging because Solidity evolves very rapidly with frequent syntax and feature updates. It's a moving target for formal methods. On the other hand, EVM is too low level. It's like verifying machine code directly. Now, this is where YUL fits perfectly because it's a stable, minimal, and well structured intermediate representation, which is much easier to model and reason about formally. This is why I chose to formalize YUL. It gives the best balance between real world relevance and mathematical clarity. Now, the hypothesis is how can a machine checked formalization of YUL in Isabelle, which is a theorem prover, can eliminate compilation ambiguities and prevent smart contract exploits? The idea is if we can somehow create a machine checked mathematical rigorous model of YUL in Isabelle, we can prevent compiler bugs and reduce the risks for exploits. Isabelle is a very trusted proof assistant where each proof and function is machine verified, which is why we chose Isabelle. Now, the goal is not to just write programs, it is to prove that they behave correctly, providing guarantees that Solidity alone cannot provide. It helps in basically reducing compiler-induced bugs and end-to-end verification. The aims of this project is to specify the semantics of YUL and Isabelle and work towards a formal real-world contract. Now, to ensure that this formalization was accurate, I followed a very practical process. I started by writing YUL programs and test cases in Remix. Remix is an online Solidity IDE, and it allows us to compile Solidity code and view equivalent YUL output. This helps us understand how Solidity behaves, including outputs and its edge cases. After that, I re-implemented the same logic in Isabelle, defining how each instruction works and writing formal proofs for them. Finally, I compared the results, the outputs from Remix and the outputs from my Isabelle proofs, and they matched exactly. These gave me confidence that my formal method was correct. It behaves just like real-world YUL execution. Now, the software that we used in this project was Isabelle, obviously, along with JEdit, which is an interface which I used to write and manage the formal definitions. I used Remix, which I discussed was an online IDE for Solidity, and finally I used Git for version control. My approach to this project was inspired by the philosophy of test-driven designs, which I applied to formal methods. I started by testing each small function like memory, storage, or arithmetic functions directly in Remix. Then I wrote the same logic in Isabelle, created formal unit tests or lemmas to make sure that they behave in the same way. Once these results matched, I moved on to more complex snippets, compiling multiple operations and proving their correctness end to end. This gave me confidence that my Isabelle formalization is not just theoretically correct, but it reflects the practical YUL execution as well. Now, this is an example of a simple program that I had formalized, which is storage. This is a fundamental block as it is used in many places, and even it is used in parts of the ERC20 smart contract, which we did. In this example, we can see that store 042 basically stores the value of 42 in the slot 0. Then slot 0 reads the value back. We get 42 again. On the Isabelle side, I defined store as a function which updates storage mapping and assigns the value to a slot. Then slot simply reads it back. Then the lemma is pretty simple. I just store the value of 42 in 0 and then I read it back. I should get 42 itself. This is a kind of very simple verification and it's a starting point. I applied the same process to arithmetic, ERC20 logic, which I'll show next. Now, apart from formalizing storage in Isabelle, I also formalized memory, which I modeled as a list and created functions to read, write, copy from it. I formalized arithmetic operations like add, subtract, multiply, divide, etc. I also formalized parts of the ERC20 smart contract, like balance transfers, like storage, safe addition, and all these sorts of things. I also wrote unit test lemmas that confirm that they match the actual execution in Remix, which is very important. Now, the things that I've achieved so far, I've formalized 4 standalone YUL programs covering ideas like arithmetic flow, storage, memory, and alongside that, I also wrote 12 helper functions for these 4 programs, which support things like arithmetic operations, memory manipulation. I also managed to formalize a small part of the ERC20 smart contract. I tested this parts of the smart contract thoroughly in Remix to understand their behavior and built matching formal definitions and unit tests. Lastly, I wrote lemmas at unit tests for each function. These confirm that the proofs act exactly as expected. Now, looking ahead, one of the key goals of this project is to extend the full verification of ERC20 smart contracts with thorough unit tests and covering all major functions. This could show that this formal verification can scale to major projects. Another important step is to write mathematical proofs for properties like safety, consistency in the contract behavior. We can rely on mathematical proofs more rather than just writing unit test lemmas. And apart from this, I would also like to set up a CI/CD style pipeline where every change to the formal model would automatically rebuild the entire proof in Isabelle, cross-validate our compiled YUL and Remix and other tools if we use them, and also run all the unit test level checks. Lastly, to wrap up, this is the first formal verification of YUL in Isabelle, and this closes a major security gap. And it's like working towards making blockchain systems more trustworthy. Secondly, this is not just about formalizing one or two functions, it lays the groundwork for reasoning about full smart contracts and even full protocols. And importantly, it gives developers a chance to catch bugs even before they are deployed. What makes this project special is this is one of the first formal verifications of YUL in Isabelle, which is very exciting and challenging to work on. Lastly, that was all. Thank you. I hope you enjoyed it.